Welcome to Module 5 of our workshop. This module is called Dimensions. So far we've discussed how digital images are formed, how pixel values are stored, and how image data can be visualized using different lookup tables. In this module we're going to expand our understanding of images beyond simple two-dimensional representations. Modern microscopy datasets often contain much more information than just rows and columns of pixels. Images may contain multiple fluorescence channels, multiple focal planes, time points, or combination of these dimensions. Understanding image dimensions is essential for accurately measuring biological structures and effectively working with multiplex immunofluorescence data in QuPath. In this module, we'll focus on three key questions. First, how do we calculate physical distances between pixels? Second, how can we interact with images that contain more than two dimensions? And third, how can we summarize information across multiple dimensions when the data becomes too complex to visualize directly? By the end of this module, you should understand spatial calibration, know how to work with multidimensional images, and recognize when image projections can be used for data visualization and interpretation. Let's begin with spatial calibration. When we look at a digital image, we're viewing pixels arranged in a grid. However, pixels themselves are not inherently meaningful units of biological distance. To convert measurements into real-world units, such as micrometers, we need spatial calibration information. Spatial calibration defines the physical size represented by each pixel. For example, if one pixel corresponds to half a micrometer, and then we're measuring 12, then this comes to 6 microns. Without spatial calibration measurements such as cell size, nuclear diameter, tissue thickness, or distance between cells, these cannot be accurately interpreted. Different imaging systems often have different spatial calibrations. For example, here at the MapCore core facility, we have a cell dive multiplexing imaging solution. And when we acquire an image at 20 times magnification, the pixel size is approximately 0.325 microns per pixel. On the bright field scanner, from A22 scanner, this produces with a 20 times magnification a pixel of 0.4987 micrometers. And when we go to 40 times magnification, it comes to 0.2525 micrometers per pixel. So this is an important consideration, that even a microscope at the same magnification level doesn't necessarily mean it has the same spatial calibration. This is why two images acquired at different magnifications cannot be directly compared using pixel measurements alone. Always verify the spatial calibration before performing quantitative measurements. Up to this point, we've mostly discussed two-dimensional images consisting of x and y coordinates. However, microscopy datasets frequently contain additional dimensions. A fluorescence image may contain multiple channels, often represented as the C dimension. A Z-stack contains multiple focal planes, adding a Z dimension. Time-lapse experiments introduce a time dimension, sometimes referred to as the T dimension. When combined, these dimensions create multidimensional datasets that are sometimes described as n-dimensional images. Understanding which dimensions are present is important because it determines how we navigate, visualize, and analyze the data. When images contain a Z dimension, we often think of them as volumes rather than flat images. One approach to exploring volumetric data is volume slicing. Volume slicing allows us to examine individual planes within a three-dimensional dataset. You can think of it as looking through successive layers of a biological sample from top to bottom. This technique is particularly useful when studying thick tissues, cellular structures extending through multiple focal planes, or complex three-dimensional biological arrangements. Rather than compressing all information into a single image, volume slicing allows us to inspect structures at their original depth. For this exercise, we'll practice locating spatial calibration information. We're going to be opening 2 additional images from the ImageJ module. We're going to determine the pixel size associated with each image, and as you do this, think about where this information is stored and how QuPath might retrieve it. We're going to also consider whether there is metadata that we can access to obtain this information outside of QuPath. A key objective of this exercise is recognizing that image files contain important metadata beyond the pixel values themselves. I'll pause here to give you a chance to do this exercise yourself. I'll now demonstrate how to perform the steps of this exercise. So we're back in QuPath with our project. We currently have the fluorescence cell sample, but we need to obtain the other 2 samples in this exercise. Again, we can obtain them by going to the ImageJ and opening the ImageJ window. Here in File, we can see that there were other samples that we had accessible, and the ones that we're going to be obtaining are the HeLa cells image here. We'll now save that to a location we'll access later on, our desktop. Close. And then we'll open the other sample, which is the mitosis. Here we'll save as a TIFF, again to the desktop. We can then close both windows, and in our File Explorer, we can see that we have now 2 more images. We can use the drag and drop opening mechanism to then import the images twice at once. 2 of them at once, sorry. Here we can again set the image type to fluorescence, leave these options blank, we'll auto-generate pyramids, and then click import. This will take a second, and now we can see that we have 2 additional images in our project, the HeLa cells and the mitosis sample. So now we're going to start with the HeLa cells image as illustrated in the exercise. Clicking onto the image in the list, double clicking, we can then go to the image tab. Here you can see there's some information about the image. First, the name, where it's located, what pixel depth we have for this image, the magnification, which is currently unknown, how many pixels in the width and height, at what dimensions we're working with, so we have the number of channels, how many Z and T dimensions, which are just 1, and then the information that we're here to look for, the dimensions of the pixels in the physical units. Now let's go back to the fluorescent cells image. When we go to the image tab, we see similar information as with the HeLa cells, but now we see that there is an unknown width and an unknown height to this image. Now, you may have noticed that in the bottom right of the image, it mentions that you can press I to show info about the image. This won't work in QuPath, but if we open the image again in ImageJ and we press on I on our keyboard, we get this new window which has some additional information about the image. However, looking through this information, we still don't have the spatial calibration. This means that we're not able to measure the physical distances between, say, the cells of this image. This limits our analysis as a result. We're going to now close the ImageJ window and then go to our final image sample. Here we can see that because this is an image with a time dimension to it and multiple depths, focal planes for depth. We have options to go through the time dimension and the depth of the sample in the top left of QuPath. We can see that we have information on the pixel width and height, and also the Z spacing of our focal planes. However, we don't have a time dimension. Since this is a sample from ImageJ, we might be able to obtain the information by opening the sample in ImageJ, and again selecting I on our keyboard. And here we have some additional information about this image. And we can see, scrolling down, that we have specific information about the interval in the time dimension. This exercise demonstrates how QuPath can obtain a lot of information about an image, but maybe can't obtain all the information that may be stored alongside the image. Now we move on to what are projections. When working with multidimensional data, we often need a way to summarize information. One common approach is an image projection. A projection combines information from multiple slices or dimensions into a single image. For example, a maximum intensity projection takes the brightest pixel value observed through a stack and displays that value in the final image. Projections can make complex datasets easier to visualize and interpret. However, projections should be used carefully because information about depth or dimensional relationships may be lost during the process. The usefulness of a projection depends on the scientific question being asked or whether specific tools require a way of compiling the information across the dimensions. Let's revisit our learning objectives. We discussed how spatial calibration allows pixel-based measurements to be converted into meaningful physical units. We explored multidimensional image data and identified common dimensions such as channels, Z-stacks, and time points. Finally, we examined projections as a way of summarizing information across dimensions. These concepts are fundamental for working with modern microscopy datasets and will become increasingly important in advanced image analysis workflows. To conclude, here are the main take-home messages from this module. First, image metadata are just as important as pixel values and should always be preserved and reviewed. Second, if we want to measure physical distances or object sizes, we must know the spatial calibration of the image. Third, it is important to determine whether pixels are isotropic or anisotropic, in other words, whether pixel dimensions are equal in all directions or differ between axes. And finally, projections can provide useful summaries of multidimensional datasets, but they simplify the data and may discard information relevant to specific analyses. Understanding image dimensions and calibration will help ensure that image measurements are accurate, reproducible, and biologically meaningful as we continue working with multiplex immunofluorescence data in QuPath. That brings us to the end of this module, and I hope you'll join us for our next module about image data formats.